So I'm actually not leaving, I'm staying here, but I'm going to give an exit presentation for fun. So I'm not sure everyone was here when I had my first thing here, so not everyone here knows me. I'm Casey. I got my bachelor's from MIT in 2015, and I'm a PhD student at Virginia Tech right now, doing uncertainty in modified aircraft configurations. So I'm from near Asheville, North Carolina. If anyone knows where that is, that's not where I'm from, but I'm from close by. The fun fact along with that is at my house, we have pigs. So this is Juliet when she was a baby. She's our inside pig. So she's like a dog, but she's a pig. So kind of an introduction to all of this. I just was on the internet yesterday and was looking at all of the articles on autonomy that are out there all the time. My favorite here is that I did get a Chipotle burrito from a drone, I guess 2 years ago while I was at Virginia Tech, which was really exciting. And then yesterday the headline was this. Now for the hard part. And I was really hoping that the hard part would be something about uncertainty, since that's what I care about, but it wasn't. So now, why uncertainty matters and why that is the hard part. So humans are very skilled at adapting to changing conditions. When we're talking about autonomy, they are either going to have to adapt themselves just like humans do, or we're going to have to program each and every condition into that. Both of those are hard problems. Trying to program every condition is probably a little bit infeasible. Another big aspect is that autonomous aircraft systems are safety critical. When airplanes crash, people die or get hurt, and that's really important, and we can't really have that if we're going to have a large number of autonomous vehicles. And especially with the work for a tractor, accounting for, adapting, and communicating the uncertainty that the autonomous system is seeing is a very large part when we're talking about the trust that's in the system. If we can have sort of a two-way conversation with it, then we know whether we can trust the system or not. But the system also has to understand uncertainty, and we have to understand the uncertainty that it's trying to tell us. A big aspect about how we as humans tend to understand uncertainty is that there's a difference between uncertainty and risk. So uncertainty is just the likelihood that something's going to happen, and then risk is, given that it happened, what's the consequence? What comes out of that? They're very closely related, but they're not really interchangeable, even though we tend to use the words that way. So the example I have here is there might be a high probability that you slip on a banana peel, but there's a very low risk that you're going to die from slipping on a banana peel. And the important thing is both of them need to be addressed for autonomy, but uncertainty is kind of the first step, because you need to know how likely some of these things are before you get into what's their effect and how catastrophic or not they're going to be. At the beginning of the summer, we kind of set this approach to go through and really look at uncertainty as a whole for autonomous systems. So one of the big things is Natalia and I wanted to make a comprehensive list of all of the uncertainties in autonomous systems. And it sounds like a very lofty goal, and I've read a lot of papers this summer, and it's something that's really missing for autonomous aircraft. We have a lot of literature on some forms of uncertainty, but as a whole, we haven't sat down and said, these are the 1 million uncertainties that actually are present. The next step is sitting and looking at those uncertainties that we've identified and determining what kind of uncertainty they are, and then if there's anything we can do to reduce that uncertainty. There are some types of uncertainty that are better than others, but the important part is, can we reduce them, can we handle that, and what can we do to identify the uncertainties that we are currently bad at, which leads to the next step, or I guess I skipped 3, to go down to 4, which is to find the areas where we currently don't have mitigations and can't reduce uncertainties, and we're almost problem uncertainties. We don't know what to do with these uncertainties, but we're going to need to find a way to address them in the future. To make this a little bit easier on myself, when I started, I began with this scenario of an autonomous aircraft operation. So we have an autonomous aircraft that's going from point A to point B, and it has to navigate the environment. There are stationary actors, we have a tree, we have buildings, there are moving actors, people, birds, weather, and importantly, there can be also other autonomous aircraft out there. And one of the big things is you don't necessarily know whether they're good guys or bad guys. There can be negative actors in your environment as well, and that all adds to the uncertainty that an aircraft would have to handle as it did its trajectory. So I have a giant list in my office of all of the identified uncertainties that I've come up with. And one of the really important things that I wanted to do was ensure that we got all of the uncertainties, even the ones that kind of seem silly or that, oh, we always ignore that. Because I think one of the things that is going to become increasingly important is a lot of the things that have previously been ignored are going to come back and have a really large effect. So some things are like knowing the exact position of the vehicle. Well, we're used to using sensors. We're used to the kind of results we can get using GPS or using LiDAR, but that might not be enough for what we need to do, and we need to realize that we don't actually know the exact position. We're basing it off of estimates from sensors that have their own accuracy. The next step was to sit through and make a types of uncertainties. So there's a lot of different uncertainties on this list. I won't sit here and read them all to you. The important ones are kind of the ones that are in red. So we have probabilistic with an unknown distribution. So that's saying I know that it has a probability distribution attached to it, but I don't really know what it is. It looks like a normal function, but I don't know the mean, I don't know the variance. Bounded values are also a problem. If I only know that it's between 1 and 3, but I don't know the value in between there, that's another type of uncertainty that's very difficult to handle. My personal favorite is possibilistic, so that's whether or not the event can happen. So if it's something that's very unlikely, you don't really have enough information to characterize it to get a probability distribution function for it. And it kind of seems like it comes out of the blue, even though it might have that small probability that we're just adjusted to ignoring. A key one that's down at the bottom here is unknown uncertainties. So these are uncertainties where we don't really know anything about it. And sometimes that even means we don't know what the uncertainty is. Almost by nature, if you can identify it, then it's no longer unknown because it has a name. So these types of uncertainties are something that's very difficult to work with because you don't know what they are, but it's still something that we need to be aware of, that there are these cases that we will never know about almost until it's too late. And then we also have moral ethical uncertainty, which is kind of the classic trolley problem. And that's another part of uncertainty that autonomy in general will have to tackle. I also went through and looked at the different mitigation types that can apply to these uncertainties. A lot of them are mitigations that we're all very used to. If we need more data, we go and add sensors. If we need redundant communication, we know how to do that. The important thing here is figuring out which of the uncertainties that I previously identified that these mitigations don't work as well on or are not getting those uncertainties to something that we are able and more used to handling. So how I did this was I went through all of the uncertainties and I went through and classified them in the types of uncertainties. So we have 3 examples here: the exact position of the target, mission planning system errors, and then the mission impact on performance. And I classified these into the categories of uncertainties that I showed previously, and then I could add mitigations to those. So example, for the exact position of the target, as I mentioned, that exists. There is a goal target somewhere, but you might not know exactly where it is at. So maybe you need to communicate with the target, maybe you need sensors where you can sense where the target is, but you still are needing to apply those mitigations. You just don't automatically know where the position of the target is. Once we've applied these mitigations, then you can kind of see the uncertainty evolve over time, and we end up with new uncertainties. So for the position of the target, we then, once we have sensors, then it becomes more of we have a tolerance on it, or maybe if we have extremely good systems, we can know the exact position based on those mitigations. But one of the problems here is we get some uncertainties where these mitigations still leave us with unknown uncertainties or bounded uncertainties and other difficult uncertainties. One of the ways we wanted to explore these difficult cases where current mitigations aren't really enough to get the uncertainties down to a suitable level is looking at case studies. So taking these difficult cases, kind of writing out mini stories and seeing what's the ideal information that I would need, and then trying to find where the technology gaps are to get those uncertainties down to a suitable level. And there's a number of them that I've been working on. Today I'll just be talking about unexpected events. I showed this one yesterday as well. But the idea here is that we have 2 autonomous aircraft that are flying in the middle of fog. Both of their communication systems have gone down, so they can't communicate with each other or the ground, and they're just somewhere out in this fog. So one of the things here, this is hitting on the possibilistic uncertainty. We don't know how big the foggy area is, but maybe they're a mile apart and have no chance of hitting each other. Maybe they're 5 feet apart and are about to crash. But we have no way of knowing that because of this fog. There's some mitigations we can use in this scenario. If it gets foggy, the aircraft just have to land. You can't fly if it's foggy. Or once your communication system has failed, you have to land. And these mitigations work, but then it gets to, what if this autonomous vehicle has a very important mission? What if it's doing search and rescue? What if it's delivering an organ to someone who's about to die? You may not want it to land. You may want it to be able to continue its mission. So then you have to step back and see what else can we do for this scenario to somehow reduce the uncertainty and get a better idea of what is the correct thing to do. So since I'm not leaving, and I unfortunately don't really have a conclusion because it's still ongoing work, but we have made a comprehensive list of the uncertainties for autonomous systems, and I've started going through and classifying those uncertainties and looking at the mitigations that are needed to get them to uncertainties that we can handle, that we know what to do with. And as I mentioned, we've been working on these case studies to start tackling some of the harder uncertainties and finding where those technology gaps are to start bridging the gap between what we have now and what we're going to need in the future. So as I'm staying for the fall, the things I'll be working on are just continue getting more uncertainties. It's a never-ending list of uncertainties by definition. One of the things that I really want to start is looking at risk. Because I mentioned at the beginning of the presentation, it's not enough to just look at uncertainty. We really need to be finding the areas where we have high uncertainty, but also a high risk. And those are areas where mitigations are especially needed. And then, of course, this all goes back to the idea of building trust in autonomous systems and being able to kind of share the uncertainty with the system and know where the uncertainty lies and what we can do about it. So this is something my old branch did that I really like. So they always have the summer interns share what they did while they weren't at work for the summer. So I have a few pictures. The most exciting thing for me is I bought a couch. For the first 2 months I was here, I had lawn chairs in my living room. So very exciting, now have a couch. I got to present at the Langley Expo and teach a cross-stitching class, which is something that I'm very passionate about. Somehow, after 6 summers here, it took the 6th summer until I was able to go on a gantry tour, but I was finally able to get on a gantry tour. And I also got to go out to AIAA Aviation as a diversity scholar and get a week's paid conference and vacation for that. So that was pretty fun too. So any questions?
So my question might be further down the line in your research, but so I'm thinking about when you're probably going to be looking at vehicle types for the risk and uncertainty analysis. Will you like quantify the questions about a vehicle based on the job that specific vehicle would do? For example, if the airplane, let's say, is going to be flying in a very low population area the whole time, will you quantify the risks differently than if it's going to be doing obviously flight over a heavy populated area?
Yes.
And
so
it's going to be a case-by-case basis?
Yeah, so that's one of the reasons why we wanted to initially start with identification of uncertainties separate from the risk, because the same uncertainties exist everywhere, but the risk that's attached to those uncertainties, that part is also going to vary. Because like you said, there's always going to be the uncertainty of a meteor crashing on of a building being there, but it's obviously that risk is going to be lower in a rural setting than in a city setting, but the uncertainty is still there. So when we were just identifying the uncertainties, we wanted to kind of enumerate them and then go back and say, for this vehicle, these are the uncertainties we know we're ignoring, but acknowledge the fact that they're different based on the scenario.
So the title of your talk is Uncertainty and Risk, and you said towards the end that you were eager to turn your attention towards risk.
Yes.
What are your thoughts on the relationship between them? Any insights you've gained so far? I know it's early, just wondering what.
So I think the biggest part with risk which was what I was just speaking to, which is that part of the risk is going to be acknowledging that these are the uncertainties that we are kind of ignoring for this specific scenario. But then once you get into talking about risk, at least in my mind, I kind of envision it as kind of a mirror framework, as there's going to be a list of uncertainties and a list of risks. Not all of them will apply every time, but I kind of see it as a mirror framework to this, and then together they're kind of capture everything.
So I'm only used to dealing with bounded uncertainties because I've worked before with dynamical systems, and part of what people do with dynamical systems and bounded uncertainties is they classify them in two types: matched uncertainties, which span the input matrix, and unmatched uncertainties, which do not span your input matrix. But this is a very specific kind of systems, and you're dealing with much more generic systems that are decision making. It's just not a dynamical systems. So I was wondering if you would be interested in looking at extending the concept of uncertainty or disturbance compensation in the case of dynamical systems to a larger set of systems, and if you've looked into that or something.
So we haven't looked into it specifically. There's a lot of literature, but you talk about robustness, resiliency, reliability. So you have all of these R's, and I think they're all.
Is that one of them?
Yeah, there's five. There's 5 or 6. I don't know. But all of these things, and I think I don't want to get too much into treading on the robustness part of it, because that's a separate issue from just does the uncertainty exist. Obviously, we try and build robust dynamical systems that can handle these types of uncertainties, but that is a separate question from whether they exist or not. And a lot of times, it's very difficult to even know if they're bounded or not. With my PhD results, we treat things as bounded uncertainty, and we're making up those bounds.
Yeah.
for estimating them.
If the uncertainty has a physical meaning, then you can say it's bounded, right? It's safe to assume that the uncertainty is bounded, whether it's when or how far from what you estimate an object is and things like that. But if it's some sort of another types of uncertainty are bounded, like is does my code have an error and it's going to go to infinity or divide by 0 and things like that. So.
On your probabilistic unknown distribution,
Mm-hmm.
how do you know it's a normal distribution?
So there are some cases where you might know some amount of information. Sometimes you can tell that things are behaving in a probabilistic manner, but it's very difficult to get accurate measures. Think about if you're drawing samples from a population. You assume that it's probabilistic, but it could take a number of samples until you get the accurate distribution.
But
So
it's
if you
not
have,
necessarily a normal distribution, right?
this is just an example.
Okay, so you're not saying it has to be a
No.
normal. Okay,
No.
gotcha.
Any sort of probability distribution, but the key here is that it's not fully defined. We don't know all of the parameters.